is dependent on temperature, and the rate constant is only good at a certain temperature. What we're going to do now is we are going to find out what that rate constant would be at different temperatures. And in order to do this, we need to use something called the Arrhenius Equation. And this Arrhenius Equation shows the relationship between the temperature of a reaction and the rate constant. One thing we need to do is identify the different components of this equation. EA represents the activation energy. We'll talk about each one of these separately later on in this video, but I just want to label everything right now. The units for activation energy are in joules per mole. The temperature is represented as well. Of course, we need to represent the temperature if we're going to find the relationship between temperature and the rate constant. That's going to be measured in kelvins. The gas constant is R. You've seen this gas constant before, but it was probably a different number. You probably used 0.0821 liter atmosphere mole K over mole K. In this equation, we will use 8.314 joules per mole K because we want to incorporate joules in there. The A is called the frequency factor. We'll get to more about A later. And all of this, if we take A times E to the power of that fraction there, we will get the rate constant. And that's K. That's the constant that we've been looking at in all of the videos on kinetics. Now back to that activation energy. This is the amount of energy that must be put into all the reactants in order for them to turn into products. So reactions don't just happen by themselves. They need some sort of input of energy to get them started. And usually the higher the activation energy, the slower the reaction, because it takes more energy to get that reaction started. Now the energy put in is used to break bonds, weaken them, or even rotate them. And when the bonds are broken or weakened or rotated, a new molecule, kind of a new molecule is formed, and this is called the activated complex, or sometimes called the transition state. It's a very high energy, very unstable molecule with these broken or weakened or rotated bonds. So let's just say we have all of these reactants and they're together, and now we put some energy in, and according to this chart we have to put in 30 joules of energy just to get that molecule to have weakened or broken bonds so that it can react. Remember that new molecule that's formed is called the activated complex. We can never really isolate the activated complex because it's just so unstable that it will want to form products as soon as that activated complex is created by putting in that 30 joules of energy. Now, once that activated complex is made, this reaction will release 60 joules of energy. So a net of negative 30 joules. So that's our total change in energy is negative 30 joules. Because remember, we had to put in 30, we got out 30, and then 30 more were released. That makes this an exothermic reaction because the products are lower in energy than the reactants. Now let's look at something called the frequency factor. This is symbolized by the letter A, and it's the number of times the reactants approach the activation barrier in a unit of time. Now, an approach can mean many things. Maybe a collision, maybe a molecule's rotating or twisting, somehow getting to the point where it's possibly going to react. Now, just because the activation barrier is approached doesn't mean it's reached. Think of it like you're rolling a ball up a hill. Just because you're rolling a ball up a hill doesn't mean that it's always going to get to the top of the hill. Now, the exponential factor is the amount of times it gets to the top of a hill. So the exponential factor it's a number just between 0 and 1, and it represents the fraction of molecules that have enough energy to make it over the activation barrier. So if the exponential factor is 1, that means every single molecule that attempts to make a reaction actually does make a reaction, and it's never really going to be 100% of the time. So the exponential factor is this e to the power of all of these numbers. And one thing that you'll notice is you'll see the e to the power of EA over RT. The exponential factor increases with increasing temperature, and it decreases with increasing activation energy. So that means the hotter a reaction, the more times it will actually approach the top of that hill. Now let's take a look at how we can use experimental measurements. A plot of the rate constant versus the temperature. It shows that the relationship between the two is not linear. And in this course, we like to have things that are linear because it allows us to use algebra. If we're not using algebra, then we have to start using calculus, and that makes things tricky. So we're going to manipulate these values so that we can make them give a straight line. Now, if we plot the natural log of the rate constant versus the inverse of the temperature in kelvins, that will give a straight line. Now, the straight line has a slope of negative EA over R and a y-intercept of the natural log of A. So check this out. This is, it follows the pattern y equals mx plus b. And we can find all of the information that we would need to know about temperature and rate constant using this equation. And we can plot data and create a graph so we can find this information. So what I've done here is we have some information from a chemical reaction. I'm using Excel to find the natural log of the temperature, the natural log of the rate constant, and 1 over the temperature, because those are the two items we need to plot. We can't just plot temp and rate constant. We have to plot the natural log of the rate constant and 1 over the temperature. So my x-axis, my x values are going to be 1 over the temperature, and my y values are going to be the natural log of the rate constant. And now look at this, I have a straight line, and my trend line is added, so I'm going to display the equation on the chart here. My equation is y equals a negative 11,201x plus 26.79. That equation is going to be the important part of this. So what I want to do is I want to use this experimental data to pull out information. So I'm going to rewrite this equation here. Natural log of k is equal to negative EA over R times 1 over t plus the natural log of A. This is my y equals mx plus b. So I'm going to take my equation that I got from graphing all of this data and plug it in kind of underneath each piece here. So y equals negative 1.12 times 10 to the fourth x plus 26.8. Now I want to determine the value of the activation energy. So this problem has me determining the value of the activation energy. Well, I can use my plotted data and this equation to solve for the activation energy. So negative 1.12 times 10 to the fourth is equal to negative EA, or the activation energy, over R. R, remember, is 8.314 joules per mole K. So if I just take 8.314 times negative 1.12 times 10 to the fourth, the activation energy, by the way, the activation energy is also written as a negative, so the two negatives cancel out. And I get 9.31 times 10 to the fourth joules per mole. The kelvins cancel out because they're actually multiplied by 1 over temperature, so that doesn't get included in my activation energy. So 9.31 times 10 to the fourth joules per mole. I used that equation and my data to determine this. The next thing I want to do is calculate the value of the frequency factor. So number 2, the frequency factor is A. But what I do know, I don't know A, but I do know that ln A, the natural log of A, is equal to 26.8. So A must equal e to the power of 26.8. So e to the power of 26.8 is 4.36 times 10 to the 11th. The units for the frequency factor are going to be the same as the units for the rate constant. So meters to the negative 1 times seconds to the negative 1. So A, my frequency factor, is 4.36 times 10 to the 11th per meter second. The last thing that I want to do here is predict the rate constant at 298 kelvins. So I have all of this information for different temperatures and rate constants. I want to use this equation and solve for a different temperature. So I want to know what the K is at a different temperature. So I plug in that temperature in the T, 1 over 298 kelvins. And then I will use my equation, literally y equals my equation, to figure that out. Now the y part is the natural log of K. So the natural log of K is equal to negative 10.783. I just typed all of this into my calculator. the natural log of k is equal to negative 10.783. So that means k is equal to e to the power of negative 10.783. So that means k is equal to 2.08 times 10 to the negative fifth meters to the negative first times seconds to the negative first. Those are the units for our rate constant. Now, does this make sense? Well, 298 is less than 600, and our rate constant is less than 3.37 times 10 to the negative third, so that does make sense. You have to make sure that your result is consistent with the data. Now, what if you don't have a whole bunch of experimental data, but you only have 2 different points? Well, if you have 2 different points, you can use some mathematical properties of a line to figure out what your activation energy would be. So we're going to use the 2-point equation. It's really the 2-point slope equation. So if you don't have the capabilities of using Excel and finding a graph and finding the trend line and using the best fit line, you can actually just use 2 different points using this equation. The natural log of K2 over K1 is equal to EA over R times 1 over T1 minus 1 over T2. And this is really just the point slope equation, the 2-point slope equation that you learned about maybe in math or algebra or geometry class. It just looks a little different because now we have natural logs and k's and t's in there, but really it's just the equation of a line. It's solving for 2 different points. Now I'm going to assign values to each of these numbers because I want to be able to go back quickly and look at, okay, what's my T1, what's my T2? So my T1 is 701, my K1 is 2.57, my T2 is 895, and my K2 is 567. I'm going to leave out units here because what happens is those units end up just getting canceled out anyway. So ln 567 over 2.57 is equal to EA over 8.314 times 1 over 701 minus 1 over 895. And those are in kelvins. Those temperatures are in kelvins. And that'll help us cancel out kelvins when we use that 8.314. So the natural log, and I'm typing all of this into my calculator, the natural log of 567 over 2.57 is equal to 5.396. EA over 8.314 times, and then 1 over 701 minus 1 over 895 is equal to 0.000309. What I'm going to do now is I'm going to divide both sides by 0.000309 so that I can get rid of it on the right. Ultimately, I want activation energy to be alone by itself. So I'm going to multiply both sides by 1 over 0.000309 or divide by 0.000309, and I get 17,451 equals EA over 8.314, which means that my activation energy is 1.45 times 10 to the 5th joules per mole. So the next thing I want to do is use that activation energy to predict the rate constant at a different temperature. So what I need to do is I need to assign 525 kelvins as a different temperature. I'm going to assign this as my T2. So 525 is now going to be my T2, and I'm going to find the K2 that is associated with this T2. So I will rewrite my equation so that I have the ln over ln of K2 over K1. Now my original K1 is 2.57. I'm just going to keep that one as my K1. And that is going to equal, and then I plug in my activation energy, 1.45 times 10 to the 5th joules per mole, over 8.314, the gas constant, 8.314 joules per mole K, times 1 over 701, which is my T1, minus 1 over my new temperature, which is 525 kelvins. So I'm going to type that whole thing into that whole right-hand side into my calculator. The left-hand side I'm just going to leave for the time being. The right-hand side, if I take 1.45 times 10 to the 5th divided by 8.314, and I multiply that by the difference between 1 over 701 and 1 over 525, hopefully I didn't type anything into my calculator wrong, I get negative 8.345. So then if I take e to the power of both sides, that gets rid of the natural log. So e to the power of negative 8.345 is equal to 2.374 times 10 to the negative fourth. Now I'll take that and multiply that number by 2.57 to figure out my K2. So my K2 is 6.10 times 10 to the negative fourth, m to the negative 1, s to the negative 1. And so you can use either form to find different pieces of information. You can use, if you have a whole bunch of experimental data, you can plot it and find the equation of the best fit line, use that. Or if you have 2 points, you can use the 2-point equation and just substitute in the numbers that you do know and solve for the numbers that you don't know. Solve for the number that you don't know.